Well, hello everyone. My name is Tim Ward and I'm from Kentyou, and I'm here to tell you that time is running out, which is a really cheery thing to say on a Tuesday afternoon. But the important thing is that it's running out, but we're not there yet. There's still time for us to do something about it. So I'm here to talk to you about what's going on in cities and the problems that they're facing right now. So cities are about 2% of the world's surface. It's not very much, but they have 55% of the world's population in that very small area. And as a result, they are an extremely concentrated place for the creation of greenhouse gas emissions. That's about 60% of all of humanity's emissions are coming from that 2% surface. So even though it doesn't necessarily sound like 60% is disproportionate for the 55% of people living there, the fact that it's all happening in such a localized space is a real problem. And you can see behind me we have a kind of breakdown of what most of the issues are in terms of man-made greenhouse emissions. And road passenger and road freight are really the big hitters. People talk about aviation, they talk about flying around. Yes, it is a bit of a luxury. Yes, it would be better if we did less of it. But in terms of impact, if we can do something about the roads, it will make much more of a difference than trying to do more things with air travel. And technology is what could help us to get there, right? We're all people who work with technology. We know that it can do amazing things. So we have IoT, we have AI and neural networks, we have big data that we're doing more and more to look at, and we're connecting everything together in the cloud. But all of this stuff doesn't work unless you have this raw material, which is data. Without data, all of these services are completely useless. You know, they can't do anything except with the data that we provide them. And even more critically, the data that we are providing has to be extracted from sources, and then it has to be refined. You know, the raw data that you get with the errors that it contains, with the spurious events that shouldn't really be there, with the noise that happened to come in on the sensor that gives you a reading that tells you that not only are the people suffering from a heat wave, but actually they've been flash cooked. You know, those things need to be recognized and removed, because the problem with all of these setups, particularly with things like big data and AI, is that they're only as effective as the quality of the data that you put into them. If you have low quality data, it doesn't matter how good your algorithms are, you're going to get answers that make no sense because the questions that you're asking make no sense. Now, this data that we're looking for has huge variation. So we end up with these other problems, which are that the data sources that we have are not always interoperable. When we try to find the same information about the same sorts of things, for example, in transport, often if we're querying the location of a bus, for example, we find that there is no common way to be able to get that location information that will work reliably in more than 2 or 3 cities that you go to. And because of the way that the cities have been sold these solutions, they're locked into them for a long time. And if they try and make any change to any part of the system, they find that they lose the ability to do most of the things that they could do before. So you find that this budget was spent, and then these people are stuck with effectively either continuing to pay or accepting that they're going to have to almost throw away their investments, which they don't like. And it doesn't really matter what vertical you're looking at for your city, whether it's things like transport and parking, or whether it's the utilities, or whether it's you're trying to plan or manage the environment for your citizens. Whichever part of it is, it tends to be this siloed approach where you can't move data between one area and another, depending on who within the city was responsible for commissioning the service, and you're stuck with what you had. And this is where Eclipse sensiNact comes in. So Eclipse sensiNact is a platform which is really designed to try and break this cycle of siloed data access that is not available to other parts of the city, where the real value from the data comes not from using it in that one vertical, but combining data across verticals to be able to make reasoned decisions about the city as a whole, rather than trying to make decisions in isolation without really understanding what's going on. So sensiNact allows you to integrate from these heterogeneous data sources and the different silos and gather that data into one place. You can then start to gather insights from your data sources. So you start to be able to use machine learning, use AI services, data analytics on the history, so big data processes. And those give you the ability to understand more from your data than you were before, because you have access to data across more than one part of your city. And not just geographic part, more than one vertical within your city. You can then also use this information to begin to provide more effective monitoring and control for your city. So you can actually get a real-time view of what's happening and use visualization techniques and potentially more AI techniques to recognize when you have situations occurring that you need to do something about. Or at the very least that you want to flag, you want to recognize this is not a good day, and make a note of it so that someone can go and look later and say, what was the root cause of the problems that we had on the roads today? And finally, it gives you the ability with sensiNact to run applications that are either, they can be centralized in the cloud, or you can push them out to the edge so that they can maybe run with less computational power but with a lot less latency, have low latency access to the data around them to be able to provide information to people, or perhaps be able to make decisions and actually actuate devices to try and ameliorate some of these decisions, some of these things that are going on. Even something as simple as detecting that a waste receptacle is nearly full and therefore automatically flagging to the waste management team that waste receptacle needs to be emptied. So rather than having someone who has to go round and check and waste a lot of time on ones that are maybe only 20% full, they're able to target the ones that actually need collection. So I'm here to talk to you today about some examples from the mobility domain. These are things that we at Kentyou have been working with quite closely. So it's a lot of different things that you would class as mobility. So soft mobility terminal location. A soft mobility terminal is something like a cycle hire station. So where you maybe park a bicycle and then come and someone else hires it and retrieves it later, cycles it somewhere else, parks it up there. That would be one example. You also have the dockless cycles or scooters that are available in some cities. Things that are trying to encourage people to take more active transport measures rather than increases in walking, increases in use of pedestrian or sort of person-powered vehicles rather than increasing greenhouse emissions by using more fossil fuel powered vehicles. We then have done some projects relating to traffic flow management, some relating to smart parking, so understanding and better management of parking, which is quite a limited resource in many cities, particularly if they are older cities that have narrow streets, then finding parking can actually be very difficult, and the number of vehicles that drive around looking for parking actually increases congestion and increases the need for parking, which makes it's a negative spiral that it just keeps making things worse. And then finally, an analysis of how the various things going on in your city have built together to provide a carbon impact that is maybe disproportionate to what you would expect for your city's size or the demographics of your population. So these soft mobility terminals, you can see here, this is an example actually based on Grenoble. It's the map behind me. But we've done this same operation with various parts of Paris and also in Tallinn. So we're really looking at using AI to try and optimize placement of soft mobility terminals. So the kinds of things that you need to take into account are existing commute locations. So if you have a train station nearby, then that's somewhere where you're likely to have people disembarking and then needing some kind of facility to get them to their final destination, which is unlikely to be the train station. Similarly, you're looking at things like places that people can park or get buses. We're also looking to provide social and equality and inclusion, so improving access maybe in areas where there is more social deprivation, which you can measure using a variety of different metrics that cities tend to keep on the populations within the various areas. Obvious ones are points of interest. So if you've got specific tourist attractions or places where there are maybe sporting events regularly held, those are places that, again, it can be good to give people alternative options for how they get there. And also just a basic classification of areas. So what you can see behind me with the false coloring is really just an attempt to classify areas that are urban or rural or industrial within the area, and therefore the types of people who might be going there, the times of day that they are likely to be there, and therefore what levels of cover are appropriate. And finally, you're looking at things like how much will it cost, what geographical area can we reasonably cover, and usage analysis. So these are things like from the existing setup, you would think initially, oh, I want to make sure that I cover as wide an area as possible, so I want to be as far as possible from existing terminals. And there's an extent to which that's true, but actually if you take into account usage and you see that there is an existing terminal that is regularly oversubscribed, either with too many people trying to park there, or that there are not enough bicycles and you're regularly finding it empty, then adding more capacity in the local area can be actually more productive than trying to increase coverage elsewhere. Traffic data analysis is somewhat different. You may recognize the kind of heat map behind me. So what we're looking at here is effectively trying to work out traffic density through camera analysis and average traffic speeds. And you get you get black spots where there's maybe something has happened and cars have begun to stop. Red spots where there's effectively queuing traffic, and then green for normal flows, and then areas where there's not really much car detection obviously don't get coloured. The thing that you're really looking for with a heat map like this is obviously bottlenecks. You're looking for large areas of red. And significantly, although a view like this is really nice for a human and it gets them to say, oh look, this area is bad, what's actually more important is the facility that we developed to build up heat maps that base on things like commuter hours across the past 6 months, where you get to remove individual daily issues. So maybe there was a car accident in an area on a particular day that makes it look like the worst traffic black spot in the whole of your city. But if you average it out across a 6-month period, you find that actually that area is normally pretty good, and the things you need to worry about are elsewhere in the city. So it's being able to take into account not only live data, which you use for things like real-time decision making, but also the longer-term historical data that you're using for making decisions about longer strategic changes to the way your city is running. So this is where the temporal analysis comes in. Things like seasonal variation. Does your traffic change dramatically if the weather is wet or in the colder months? And then the spatial analysis, which is checking and seeing which roads are regularly worst. Is it always in the same area? If it's always in the same area, is it a capacity problem? Or is it actually that the people are getting here, there's a capacity issue on a road that they're trying to get out to? Or do we just need to actually reduce demand to get into that area, either by pedestrianising a road, which can surprisingly improve traffic flow dramatically, or, for example, by trying to provide more other transport types. So this urban mobility hypervisor, which is providing these sorts of bits of information in heat maps, we've worked across a number of different cities. So Paris and Amsterdam, Helsinki, Tallinn, Stavanger have all been places that we've done work to identify how traffic is flowing and how that fits with their public transport systems and their soft mobility systems, and whether there are changes that they could make to move more people out of cars. So this is a combination of, as I've mentioned, real-time monitoring of the traffic and the public mobility, but also longer-term analysis based on how things are given air quality and environmental conditions. So we can determine things like, for example, in Tallinn, if it's raining, you would expect a drop in cyclists' numbers by between 20 and 30%. And that you would expect for every 1 degree that the ambient temperature drops, you would expect the percentage of cyclists to drop by about 1 to 1.5%. So those are the sorts of things that you can discover. And so you can say, okay, for the spring and summer and early autumn months, we can rely on more people cycling. But actually, we do need to look at what we can do in the winter when it's going to rain more often and it's going to be colder, to provide alternatives or to provide ways in which people can cycle comfortably despite the weather around them. We have AI-based recommendation engines that help us with this. So another thing we did in Tallinn was we attempted to identify where best to put parking zones. So if you have out-of-city park and ride, then those are relatively big infrastructure projects that require investment and planning, and you want to place them fairly optimally if you can, because if you can get more people using them, then obviously it's a better return on your investment. And one of the things that was quite fun about this one is that we programmed it in with the bits of information it needed, including the locations of existing park and ride schemes. And then we presented the results, and it turned out that actually they had just approved, although had not publicly announced in very many places, a parking scheme that was going to be within about 100 meters of one of the places that we'd suggested. So the impact monitoring tool that you can see in the bottom right is there to try and help you with the analysis when you're looking at what it is that you've done, the changes that you've made, and the impact that that has had on how your city has changed as a result. Because that's one of the other things that people often forget with their AI systems, is that it's not enough to train your AI and have it making decisions. You actually need to take a long-term look at the decisions it's making and measure the impact that they're having, and then assess that against the criteria that you had going in to see, has this been effective, or do we need to look at maybe training the AI differently? Or do we need to change tack completely and we need to provide different information such that the AI is going to make decisions that better fit what happens in reality? I mean, one of the things that I love to tell people is that AI systems are wonderful in a lot of cases, but you often forget that when they interact with a human system, humans are data that fights back. AI systems get fed with data about what humans were doing, and then they say, okay, so if we make this change in the environment, then the human flow will change in this way, and we'll be able to continue on with a more optimal system. And instead, what the humans will do is they'll identify the change, and then they'll change their behavior in order to try and work around the change. And so you end up with a battle between not only a smart system, but also a smart human attempting to subvert that system. Now, finally, I talked about parking. So we have here an example from Santander, where we have live monitoring of available parking spaces that you can see behind me, and we provide people who are looking to come and park with a route to the nearest available parking space or a parking space that is nearest to their target destination. We can give them dynamic rerouting if the space becomes unavailable or if they change where it is that they're looking to go. They can reserve the space in an effort to prevent someone else taking it ahead of them. And then we also have this prediction of parking availability. So we can identify where we think there are going to be problems with parking and attempt to maybe nudge people into parking somewhere else where they're going to have easier access. So we're moving on from kind of more traditional transport and just saving carbon onto things we can do to actually help save lives. So in the EU and the USA, there's about 50% of road accidents that will occur at an intersection, so a meeting between two roads. Obviously, there are a lot that occur elsewhere, but 50% of them occur at intersections, and they have a much higher rate of fatality than other kinds of crash. Typically because they'll involve either a pedestrian or someone who is a more vulnerable road user like a bicycle or a motorbike. So what we're doing here is real-time and predictive analysis at an intersection in Manhattan, where we have live cameras analyzing and classifying the pedestrians, the trucks, the cars, the bicycles that are going through the intersection, measuring where they're going and how fast they're moving in that direction, and doing collision analysis. So basically having the understanding that this pedestrian is walking into the path of this car, and given that the speed that they're both going, there is a potential risk of collision. Furthermore, with a pedestrian, you can analyze from things like gait, and also if you can see their face where they're looking, if they're holding something in their hands, how they're holding their body, you've got a pretty good chance of being able to identify someone who's a phone zombie. They're just looking forward and walking without thinking. And one of the things that we're moving on to next is the ability to trigger loud noise and or flashing lights from the pole containing the traffic lights, so that if we detect a pedestrian who's maybe not as alert as they should be, and that it looks like they might be about to walk out into traffic, we can attempt to do something to maybe jolt them out of their lack of attention before it becomes more catastrophic than it might be. So how is all this working? Well, I've mentioned before, sensiNact is the man behind the curtain, as it were. It's the thing that is providing us with the access to this information and the ability to make real-time decisions based on it in an event-based way, but also to gather and collect large-scale historical data and then process it. So what we have is this plug-and-play platform. It's modular, as many things in Eclipse are, but it allows us to plug in lots of different protocols for heterogeneous devices. We're talking about 20 to 30 different device protocols that we support already, and the typical time to implement a new protocol, depending on complexity, but you're looking at somewhere between 30 minutes and half a day to add a new device type that we've never seen before. So the sensiNact platform is then going to take these modular pieces and provide consistent homogeneous data access for both real-time and historic data. It can provide you event-based access, so it will actually push information updates to you as they happen, or allow you to query things that are maybe periodically updated, or that you want to get the latest value, but perhaps for a very low power sensor, it's only going to respond when you request data rather than eagerly pushing data to you. We then have different, what we call northbound standard protocols. So these are ways of interacting with sensiNact. So not only is it modular the way in which sensiNact talks to devices, it's modular the ways in which you can talk to sensiNact. So you can make use of things like RESTful or WebSocket API You can make use of MQTT. You can actually put adapter layers on top of sensiNact to make it look like something, for example, an OGC sensor things access point. You can provide different layers on top of sensiNact very easily to give you standard access to your data. We then have something called sensiNact Studio. So that's an RCP-based application which allows you to build applications that you can run on your gateway so that you can push out to the edge business logic and processing for when you need rapid response, potentially without access to cloud services. So one of the things that we often find is that there's a lot of value you can get from the cloud, but if the access to the cloud is lost and you then lose the ability to perform any of the smart functions in localities, that can cause critical incidents. They can be safety critical, or they can just cause a very significant disruption in the city. And what you want is you effectively want your edge to be able to fail safe, such that if it loses access to the cloud, it's still able to perform many of its functions, potentially without being able to be updated at that time, but it will behave in a way that is safe and allows for reasonable behavior in the absence of the cloud. So this extensible platform you can see here, we have the generic layer which allows us to talk to southbound devices. You can see we have lots of different device connectors, some of which then make use of other common libraries for protocol support. So we have obvious things like HTTP, but also NOcean or Zigbee or CoAP, all available. These then get pushed into the core of sensiNact, which is where we have our data model, which makes use of the service registry so that you can see the services that you have available and find them. And then we're exposing them through, again, these pluggable adapters that give you different protocol access to the data, depending on what you need from the rest of your cloud system or the rest of your IoT infrastructure. Rather than dictating that you must use a particular protocol, we believe you should be able to choose the protocol that makes sense for what you're trying to do. So we've got more than 20 protocols supported in the southbound layer. You then deploy the applications that you want to deploy to your individual gateways. And you can even develop your own northbound connectors if the one that you want isn't available at this stage. So we have here an example of the data model. Now, I don't know about you, but there's nothing I love more than reading UML. But what I can give you is a little highlight of effectively what that UML means, which is that we have the concept of a service provider. So a service provider is what many people would think of as a device. It's something that has a physical location, it probably has a name, it probably has an identifier by which you refer to it, and it's the thing that you would talk about connecting to. One device, one provider then has services underneath it. So those services are basically logical groupings of things that the device can do. And underneath those services, you have individual resources. So a resource is effectively something that is going to either provide you with a data value or is something that you are going to be able to trigger in some way to actuate it and have an effect on the environment. So we might, for example, have this, so we've got a weather station that's designed to be deployed somewhere where there's cellular service. So we have here the wind speed and the temperature, which are obviously capabilities of the weather station that you would probably have under the weather service. But you then also have the ability to send SMS containing data updates. And triggering that, you probably wouldn't think of as a weather operation. You would probably think of that as mobile or cellular. So that resource would be something that you would expect to see under a different service, because these services are providing logical groupings. And that's how you can disambiguate, for example, things like being able to manage the battery level of your device and understand that differently from being able to, for example, measuring the voltage at a smart plug, or some kind of other sensor. So if you have things where different resources are measuring values that have the same units and similar names, you can use services to disambiguate and understand how they fit together in a whole in the device. So we have this service-oriented platform. We have our sensing and actuating services, which are talking to sensiNact. And there are potentially many sensiNacts. It's a distributed system with gateways that are expecting to generally talk to devices that are in their local area, although depending on how it's set up, the gateway may run in the cloud and may be responsible for devices that are more geographically distributed. But in general, there'll be lots of them. These are going to provide you with data processing at the edge, but there will also be some level of composition and maybe data storage in the cloud. So this is for things that are effectively too big to store at the edge, but contain data that has been filtered and processed at the edge so that you're not overwhelming the cloud with data from every single one of your devices. And we attempt to make all of this as reusable as possible. So we have our monolithic systems that we actually try to break down into these shareable services. So the cloud services are individual and separate from the gateways, and they may be used by the gateways, but they can be deployed and managed independently and accessed by different organizations. So the data processing is then able to be business oriented, because rather than having something where you're worried about the implementation details of how you're getting the data from the various devices or what cloud technology is being used to store them, you're able to gather that information within sensiNact with a common understanding of how the data is going to be represented. And then you can use the modular nature to customize and extend your system as you add more devices, rather than having one which becomes brittle and locked in and impossible to upgrade over time. So we've talked about the monitoring and development. We have our gateways, which the developers are going to work with, but they also need to be able to monitor and understand what's happening. And this is where sensiNact Studio comes in, which is our rich client-based platform for development and also for monitoring. You can see here it gives you map views with points marking where the various devices that are available to you. So again, this one's looking at Santander. We have then Kentyou, which is a web-based portal providing some of the same monitoring function, but also some more sophisticated real-time aggregation and view over your data, including historical data. So you can see here this is data that's being collected from that intersection in New York City, and how we make use of Kentyou is something that I'm going to just show you a little bit more quickly now, so you can get a feel for what I really mean when I'm talking about real-time data. So, yes. All right, can I switch to this mic? Is that? Hi, this will probably be a little bit easier. Hopefully you can all still hear me fine. So, if we log in, you can see here we've got the portal, which is giving us, in this case, because it's a test account, it's a range of different sets of information from across the various places that we've been doing air quality monitoring. You can see some historic ozone level measurements, and actually, so this is predicted data going into the future. You can see if we look at the dates there, you can see this is our prediction for tomorrow and the next few days, based on an AI model that's been analyzing weather patterns and the amounts that have been produced in and around the surrounding area. We have something similar for carbon monoxide, where thankfully, because In this case, Livalaya is in Tallinn. Tallinn's by the sea. It tends to be that carbon monoxide, which is a relatively light gas, doesn't hang around if there's a breeze. So actually, they tend to be pretty well set for that. And what I am going to show you, however, is we have Tallinn here. So one of the data sets I can show you is what we have here, which is, so this is the live position of buses in and around Tallinn. So this is used for providing information about real-time traffic and also real-time movement of people around Tallinn. So these bus positions are things that are being collected in real time to give you the details about how things are moving in your city. And if we look a little further afield, we should be able to see over in Stavanger. We've got here real-time data where if I select in, you can see we have, in this case, 1 of 4 available slots in this cycle hire terminal. And this is, again, this is live data from the EU Open Data Service that we've been able to gather to cover the cycle network that is for the Stavanger Central, but also for the surrounding region coming from this provider. And if I zoom out, we'll see that the cycle scheme also provides us with similar information for Tallinn, and more significantly, quite a lot of cycle data for this is coming from one of the cycle providers in Paris, which covers different areas. So you can see here we have, again, more live data about available cycle hire for areas in the north, but also in the center of the city. So this information, you can combine it with other movements of people and start to use it. You can see how we're accessing this data and using it to provide information about how best to do things like extend cycle networks or extend public transport provision in order to attempt to reduce the impact that cities have on our climate. So hopefully, is this microphone still live? Okay, I'm back live now. So something that we are aware is that as a not particularly large company, we are going to be able to maybe make progress, but if we're really looking to move the needle on this one, we need to pull together, we need to gain more traction, and we need to work together to get these solutions up and running in a larger number of cities. So we're a founding member of the Urban Technology Alliance, which has 15 cities and a number of other companies who are coming together to attempt to start working on these problems and get solutions live and running, initially as test deployments, but then extended out across cities. And this is something where I would encourage people to get involved or at least look into what's happening. And while I do want you to evaluate this session at the end, actually something that I'm more interested in is if any of you here are interested in the smart city topic. So I'm going to be discussing it at the OSGI BOF tonight, because there are a number of people interested in smart city there already. But if you would come and join me, or if you aren't looking to join that BOF, if you could give me your details, are interested in becoming part of a smart city interest group here at Eclipse. So an interest group differs from a working group in that it is a much lighter weight process. So you don't have committee organization in the same way. There's no membership fee. It's something where effectively companies and cities will be coming together to attempt to identify not only problems but also maybe areas where there is the potential to perhaps collaborate on delivering something. So maybe there's a city that has some budget, but the companies that they've been talking to can't individually address the problem. It's something where we could maybe come together and start working together within Eclipse to provide a solution that will work. And the more that we can do that, the more positive our impact will become, until eventually maybe there would be a working group. But at least we'll be able to maybe start moving the needle a little more than we can on our own. So I think at that point I'm going to say thank you to everyone. I think I've probably used up all my time. So yeah, if there are any questions. Sure.
Yeah, so thank you for the talk. Very interesting. My question is, first, all of this, what you showed, is part of the Eclipse project already?
So the question is, how much of what I've shown is part of the Eclipse project? So in terms of the base gateway and the data access to all of the sensors that you've seen, absolutely everything in Eclipse. The web UI I showed you, not in Eclipse. That's a product, but that's really just map viewing on top of the existing data. It's not. There's no part of the actual back-end implementation of the system that you wouldn't be able to do with open source stuff.
And with all AI prognosis parts, they are all on the back end. So
the AI analysis, obviously the individual neural nets that we've put together are things that we've created and are commercially have been commercially bought. But that's true of any AI model that you train yourself. You've created something you own. But in terms of deploying your own AI services, it's very quick and easy. Yeah. So if you want to start creating your own AI models, then yeah, just drop them in and they'll be able to be used and reported. Okay. Well, thank you everyone. Enjoy the rest of your conference.